Look, so this work is a collaboration with Ludmila, who will be talking afterwards, Alan Hart, who is now a postdoc in Exeter, and then one of our students, James Louvre, who is in the audience. And actually there is this part of the talk at the end having to do with error bounds and so on. So he's prepared a poster and he will be showing it later this week. So some of you have already heard bits and pieces of this talk, but I wanted to present this talk today because actually the idea behind it came from Ed in this meeting that Ludmila organized a few years back in Constance. So you surely have forgotten, but she took us to this nice restaurant in this island in the middle of the lake, and coming back in the car, so Ed, he was saying, look, there are these connections between this forecasting that we do with reservoir computing and generalized synchronization. So all we did was just digging that out and putting some mathematical flesh on that idea. So that's why I wanted to give this talk today, because I was talking after you. And anyway, it's tricky because you see what I'm going to be doing is to put together reservoir computing and basically dynamics learning with extremely venerable subjects in dynamical systems, like synchronizations and topological conjugacy. So I see some of the people in the audience. So there is Juan here. I see that there is Lou Pecora in Zoom. By the way, hello. And so anyway, these are experts on this subject. So that's why I will keep a low profile and I will just try to tell you what I know for sure is true and what I think is interesting. So having said all that, so these are the points that I will try to go through, some faster than others. So this is the idea. Look, collectively speaking, in machine learning, dynamical systems, signal treatment, control theory, we are very good at either learning, estimating, approximating, call it any way you want, objects of this type, right? So what we have is dynamical covariates, and then we have this functional that takes us to this explained variable, right? So, so these are the mathematical objects that we will be talking about. So if you are doing reservoir computing, you do it with reservoir computing. If you are doing systems theory, you do it with a state space system. So there are many ways to do this, right? But this is a generic case for many examples that you have out there. So if you are into stochastic differential equations, the Ito map that gives you the solution of a control differential equation is of this form, because it's what puts together the history of the driving noise with the solution that you are going to have for this equation, right? So there's this functional of this form, this capital H that you saw before, and this is what we have to do here, right? We have to find that capital H. In that case, in continuous time. In most of this talk, I will be concerned by the discrete time situation. Also, if we go deterministic, if you are doing dynamical systems, it's the same story. So we have Takens theorem. I will go carefully through it because this is one of the most inspiring examples that we have. If you are looking at the dynamics of the observations of the dynamical system, you know that there is this delayed version of the observations that actually are able to predict through this functional of this delay map. In this case, we don't go all the way to minus infinity when it comes to the past. It's only 2q plus 1 points in the past. If you want to forecast the actual point in these observations of your dynamical system. In this case, it's a finite memory situation. So, but in any case, if you are into econometrics, or you are studying hysteresis or controlling in mechanical engineering or electrical engineering, this situation appears very, very often. So you have these dynamical variables, right? And then you have, in principle, a dependence that goes all the way to minus infinity. And then what you need is this explained variable that I will generically call YT. Anyway, the most archetypic example that you can use in order to obtain objects of this form is this state space system. So you have basically your input, then this gets embedded into these state variables through a state equation, and then out of a static readout, you get this output. If you are in the presence of what in reservoir computing we call the equistate property, that is, you have existence and uniqueness of solutions for this equation going all the way to minus infinity, you know for sure that there will be an object like this, right? That is going to be by construction causal and time invariant, and then it induces a time equivariant filter out of this equality that you see here. Actually, this is what we do in reservoir computing, right? So these equations that Ed was using in his empirics is actually an object like this, in which this is a neural network-like object, and this is just a linear readout that you estimate through a linear regression. But and this thing that you see here is something quite generic. So you can prove various theorems that are by no means the original. You see my name and Ludmila's here, but actually there are in the control literature things that are very similar to this, that show you that in the fading memory category you can approximate any object by basically the solution of a state space system, okay? This, for the control people, this does not solve the realization problem. All I am saying is that you can approximate any fading memory filter by something that is the solution of a state space equation. It's not that I am representing, I'm just approximating, okay? But this is good enough for these machine learning applications that we are interested in. This is a huge family of state space systems. Actually, it has been known for a long time in the basically electrical engineering community and signal treatment and state and systems theory community that actually you need very little in order to obtain this universality property when it comes to approximating fading memory objects. Actually, you just need, and this is something that probably in the first place I saw it is in this classical paper by Boyd and Chua in 1985, where you just need to take linear systems with universal objects as readouts, right? Polynomials or neural networks, if you want. Like this, you could obtain this kind of universal approximation for fading memory objects. So a different story is if you want to do reservoir computing type of machine learning applications. The defining properties of reservoir computing is that the state equation is supposed to be randomly generated, and then the readout, it has to be just purely linear, because you want a training which is simple, automatic, and fast, right? So if you want things sort of like that, then you need to work a bit harder than this. So there are two that are very well known to be universal with linear readouts. So the first one is a generalization that we did with Ludmila of very classical objects in basically Kalman filtering theory. So these are, if you want, affine generalization of these state affine systems that I think were introduced by Flies and Normand Sirot. So these are French system theoreticians. And anyway, you can prove that with a linear readout, this is what you see here, these kind of objects are universal as what we saw in the previous slide. The ones that Ed was using in his application are these equistate networks. So equistate networks are state space systems of this form, right? In which what you have is this neural network-like equation, and then this linear readout, right? So these are the ones that Ed was using, and they happen to be universal also, not only in deterministic situations with uniformly bounded inputs, but also with in many other contexts, right? So if you just go to my webpage and some of the people I have been working with, you will see that we have extensions. Well, this is for L infinity. You can do it for LPs. So it's the same theorems that you have for neural networks, a la Sivenko-Hornik. You can reproduce them here. In any case, something that I have to say is that what I just showed to you is not reservoir computing, because these are fully trainable structures. You need to tune every single parameter. If you want to have a randomized version of this, which is what would qualify as reservoir computing, then that also is possible. So, and that you can do either basically using traditional Baron-like spaces, and then you can prove theorems that are very similar to what you have for neural networks. Or you can do it using random projections. I think that in Ludmila's talk later, there will be something related to that. Anyway, let's now focus on the dynamical system situation. So I will be working in discrete time. So this will be my phi, my dynamical system. I will assume it is invertible. This is the flow. And then what I want to do is to learn how to forecast the observations of this guy, right? So if I want to learn how to forecast the dynamical system, is just learning the diffeomorphism. Learning to forecast the observations is more complicated, right? Because you lose information by the fact that you are using these lower dimensional observations. And then what traditionally happens, if you are lucky, is that this loss of information that you have by going to observations, you have to capture it by going into the past, right? So, and this is the lesson that we have from Takens embedding theorem, right? Takens embedding theorem, it looks like a geometric theorem. It tells you that this map that takes you from here to the delayed observations is an embedding, but dynamically, this can be used by realizing that since it is an embedding, it is an injective map, it can be inverted, and therefore you can use it in order to represent your dynamics, or at least the dynamics of the observations in a Euclidean space where the map that tells you how things move looks like this, right? And therefore, in order to learn this dynamical system, all you need to do is to learn this little f that you have in here, and that's something that you could do statically using neural networks, polynomials, or whatever, right? So I am using this as a, if you want, the inspiring example, because what I will try to do now is to make a connection between reservoir computing, or learning dynamical systems, or the dynamics of the observations of these dynamical systems with state space systems, and these classical objects that I was telling you about before, namely generalized synchronizations and topological conjugacy. Right. So for those of you who are not experts on this, let me introduce for you what I mean by these generalized synchronizations. So you have your dynamical system here. These are the observations, lower dimensional ones, right? So these are the ZTs. These are the observations of a given dynamical system. So now I take out of my pocket a state space system. In my language, these are always capital F. And then what I feed as an input are the observations of this dynamical system, right? I'm feeding the capital F with the Z's, right? The observations. So I say that there is a generalized synchronization between the dynamical system, or the observations thereof, and this state space system when the unique solution, if I happen to be in this equistate property situation of the state space system, actually can be written as a function, deterministic one, of the evolution in time of the dynamical system, not the observations, okay? So I say that I have a generalized synchronization when I have this master-slave relation between the dynamical system, again, not the observations, the dynamical system, and the dynamics introduced in a state space by the capital F, the state space equation, okay? So there is this master-slave relation. Why is this important? This is important because if this synchronization happens to be injective, automatically this implies learnability. As Takens implied for us the existence of this little map F, that if you learn it, you basically learn the dynamics of these observations in this Euclidean representation space. Why is that? Well, it's just simple, basically diagram chasing. So suppose that I have this state space equation, I fit it with these observations, then if I happen to be in a situation in which these solutions exist, well, it turns out that this map, which could be eventually very complicated, is actually giving me the next point in time for the observations out of the state at time t. So if I read out with this map H the state at time t, automatically I will produce for you what the value of the observation is at time t plus 1, right? So this is the map that, if you learn, teaches you how to forecast the observations of this given dynamical system. So that's why having these maps is very important. Equally important is that this map is invertible, because if this map is not invertible, then I cannot construct this H. I don't have this linear, static readout that gives me the forecast, right? So that's why this object that, when you look at the definition, may look a bit counterintuitive, from the point of view of learning is very important, because if you have people like that and they are invertible, then you can forecast, right? You have learnability. That's why I call injective synchronization imply learnability. So anyway, that's why something which is important, and we got the motivation from our conversation in the car that evening, is to, if you want, make the connection in this reservoir computing setup and these generalized synchronizations. These objects, as I said, they have been known for a long time. Their existence has been studied profusely. And, but if you want, in the language of reservoir computing, it's very simple to realize these synchronizations as basically the functional associated to the state space system that you are using. So, in other words, for those of you who know about this equostate property and existence of solutions, so the solution at time t equal to 0 associated to this capital F, where you feed all these semi-infinite paths of your observations, that's going to give you the value of the synchronization. So in the language of reservoir computing, coming up with these generalized synchronizations and to characterize them with the objects that we are used to is relatively simple. A different story is how these guys behave and how analytically they perform. So said differently, how easy they are going to be from the point of view of learning. Before I get into that, let me say that there is another quite trivial relation between what I just showed to you and another notion that we have in dynamical systems, which is the notion of topological conjugacy, right? So actually, if you are in a situation in which you have this generalized synchronization, so first, if this is an embedding, like it is the case in Taken situations, automatically the image of the synchronization is going to be an embedded submanifold. An embedded submanifold in the state space in which you are representing your dynamics. This may look like a fancy geometrical statement, but from the point of view of learning, it's extremely relevant, because what this is telling you is that if you want to learn dynamics using reservoir computing, you don't need to look at these huge Euclidean spaces. I don't know, for example, in Ed's papers, when he is doing all this Kuramoto-Shibashinsky, the dimension of this object is in the thousands, right? So, but actually the geometrical object where all these dynamics is living on the state space is very small, because it's actually in this embedded submanifold, right? So, so this is something that with Yanis Kevrekidis and with Boumediene we have exploited in a paper where we do this cold starting. You just basically learn this manifold and learn the association between initial conditions and the point starting from which you do your forecasting, and that increases the performance of your reservoir computing forecasting system very notably, right? So anyway, so this, there are these facts that you can get out of that. And in particular, what this tells you is that actually if you have a generalized synchronization, you have your capital F, you have your H. Actually, what you are creating is an autonomous dynamical system, and this autonomous dynamical system, which lives in this state space, in the state space of this state space system, is actually topologically conjugate to the original dynamical system that you are trying to forecast. Anyway, but I go back to the question that I was posing before. So two things that I want to show to you. The first one is that what I just said is a fancy generalization of tokens, because if you take as a state space system, basically this silly linear system where A is a lower shift matrix, so something with zeros and ones under the diagonal, and this capital C, then the solution of this system, that is the tokens delay map, happens to be the generalized synchronization that you would obtain in this context, okay? So what I just said is a generalization of tokens, in which the readout is this mapping here, right? Map that could be very complicated, not because of this part, but probably because of this part. So if you want something that we could use as a conjecture, so something that always puzzled me is why you do forecasting with tokens for the systems that, for example, Ed was presenting, and then you get things that are not that great, and then you do it with a silly ESN, admittedly in dimensions of 5,000, and then you obtain something much better. So my take on it is that what I think is happening is that by making the state equation more complicated, you are able to obtain a readout which is much simpler, right? So here we have a state equation simple, readout very complicated. When you do an ESN, you get something neural here, nonlinear, and this guy is just linear, right? So you exchange the difficulty between the two equations. This is what my take on it is, even though, as you will see in a second, there are things in what I'm saying that we don't know how to prove. So things that we know how to prove. Well, the generalized synchronizations, they were introduced in this famous PRL paper, right? But immediately, Ed and his collaborators, they noticed that the generalized synchronization, even though it may exist, it may be extremely complicated. And that's what you guys coined as weak synchronizations, right? So there were all these possibilities that, when there were all these absence of regularity properties and so on. And there was this statement that the synchronization may be wild enough to change the attractor information dimension of the response, and therefore it makes it totally useless for learning, okay? Anyway, so what we did together with Alan Hart and with Ludmila is basically we prove existence of uniqueness of these guys, both in the continuous and in the differentiable situation, and then we came up with sufficient conditions for that to be true. So if you just happen to have a state equation which happens to be contracting on the state variable, then automatically you get, of course, existence, because that automatically implies this equal-state property, and well, automatically the synchronization is going to be continuous, right? If you want differentiability, you need a condition which is a bit more restrictive, which puts together basically the Lipschitz constant of your state equation and the tangent map of the inverse of your dynamical system that you need to, that you are trying to forecast, right? In that case, you get automatically differentiability, which is, anyway, so I'm out of time. I have 4 minutes, I'm told. So then let me select, I wanted to tell you about Alan's thesis, but I have no time for that. So anyway, let me conclude with 2 short points. So the first one is that I told you before that in order for all these generalized synchronization schemes to be useful, you need synchronizations that are injective, and if possible embeddings, right? So that we have differentiability. So the injectivity, if you remember Taken's theorem, is a very complicated thing to prove. So no matter what version of the theorem you take, and this is very difficult to prove. So something that we started trying to do is that, well, for the ESNs that Ed was using in his talk, we know that there are synchronizations. We can even prove conditions under which they are differentiable. What about injectivity? What about embeddedness, right? We tried for like 2 years to do it. We never managed. So then we lowered our expectations and we said, okay, what about linear systems? So we came up with this theorem in which we were able to characterize the situations one of which is the one that is satisfied by Takens. So if you want, this is a generalization of Takens' theorem, right? And so what are the conditions under which a randomly generated linear system, so if you want a linear reservoir, would satisfy the same properties that make Takens interesting, right? And then that gave us basically this theorem in which what we needed to impose was these two conditions. The first one is basically Kalman's controllability condition, and the other one is this funny one that was coming out of trying to prove the theorem, right? And the good news is that actually, if you just draw the entries of this matrix A randomly, then generically, you are going to satisfy these conditions, right? So for this one, everybody knows, because we know that from control theory. For this one, it takes a bit more work to prove. And he's actually one of the participants in the conference of Philip. I don't know if he's here. He gave us a hint. Well, he gave Alan a hint on how to do it. So, anyway, and then the other thing that I wanted to tell you is about James's poster. So I will tell you in 2 minutes, because you see, all the theory that I gave you with generalized synchronizations is well, I give you the dynamical system, the observations, you come up with a state space system, you have your synchronization, but usually this is not how things happen. The way things happen is I give you data, and then you fit a reservoir computer to this data, expecting that the approximation is going to be good. So actually what happens is that I usually give you a functional, so this would be the functional that describes the dynamics of Kuramoto-Sivashinsky, for example, and then you fit an ESN to it, and then what you will get is that the L infinity distribution, well, out of all these universality theorems that I talked to you about in the beginning, you can make this epsilon as small as you want, but there will be an epsilon, right? So all this learning gives you an approximation, not a representation again. So what happens in there is, well, we want to know how the fact that you have this epsilon is going to spoil as time goes by, and you use this object for forecasting your forecast, right? So in any case, it's a long story, and it takes quite a few pages to prove what I'm telling you, even though what you get is quite expected, because if you want the punchline that goes at the end of all this computation is that if you run the original system, and then you run this reservoir computing system that you have learned, the rate at which these two things separate in time is going to be exponential with the Topliapunov exponent of the system. So that's something that for physicists has always been trivial, but for mathematicians it takes a while to prove. So if you go to James's poster, you will see all these technical decompositions and developments with oscillated spaces and so on. Is a very beautiful proof that he has. But in any case, this is how things go. So you have the original time series. This is the one that you have produced with this reservoir system that you have trained on the data that was given to you. Using that trained system, you construct this autonomous dynamical system, and that system, you already have it, right? Because it has been trained on data. You can compute its Topliapunov exponent, and it's actually with the Topliapunov exponent of this synthetic autonomous system that the error is going to grow. So, and it's very important that this Topliapunov exponent belongs to this trained system, because you have control on it. You have it. You know who the guy is. You can compute its Topliapunov exponent. And so therefore, you can actually give this upper bound for the error that you are committing once you have trained your reservoir computing on the data that is given to you. Anyway, I will stop here because the Boumediene is looking at me. Thanks a lot.